So happy to introduce our first speaker of the infrastructure section, Matheus, who's going to talk about double auctions for cross-chain resource allocation.
Thank you very much, everyone. So Tin already gave an introduction to my talk with shared sequencing. And so let's go. So what's the motivation? So as Tim mentioned, the motivation for shared sequencing is that the goal is to improve interoperability among blockchains. So for those familiar with transaction fee mechanisms, we are often thinking about a single blockchain, and a transaction fee mechanism is allocating resources on a single chain. So you have like blocks and you have block builders, and these block builders are allocating in the block space. But now imagine you have a scenario where you might want to execute transactions that might involve interact with multiple blockchains at the same time. So let's say you have a Ethereum blockchain and the Bitcoin blockchain, and you want to execute a transaction that might involve actually executing transactions on multiple chains at the same time. So that's the problem of cross-chain communication. One example of where this becomes relevant is, let's say you want to do a fair exchange. Suppose you have like agent Alice who owns one Bitcoin and another agent Bob who owns one Ethereum, and they want to exchange their tokens. One way that you could naively do that is that Alice could send her Bitcoin to Bob in one block in the Bitcoin blockchain, and she's going to hope that Bob is going to do the same thing for her on the Ethereum blockchain. But what could go wrong here is that because the chains are not synchronized, right? Blockchains, they cannot communicate unless you actually have transactions entering the blockchains, that Bob can just refuse to actually execute that transfer. So the goal here is that we want to execute these high-level transactions that, for example, should satisfy some security properties. For example, Alice wants to send one Bitcoin to Bob if and only if Bob sends one Ethereum to Alice. So going back in the literature, this problem has been, is not new to the blockchain domain. It's very well-studied problem in distributed systems, this idea of fair exchange of goods. And for them, this paper by Gartner in 1999 already showed this idea of an impossibility to result to actually doing a fair exchange. And the intuition for that, let me give you like the high-level idea of their model and what's different about a blockchain. Is there the intuition here is that you can imagine the system as being in a state X and Y, where X is the state of if the Ethereum blockchain, Y is the state of the Bitcoin blockchain at time T. And the idea is that you have this tuple, which is the state, and the tuple of states is fair if you never reach a point where you're not in a point where Alice or Bob owns both the Bitcoin and the Ethereum. Now, to have fairness, what we have is that we start in a fair state where Alice owns her Bitcoin and Bob owns his Ethereum, and we must end in a final state where that would also be fair. But to actually have a fair exchange, we want to have liveness, where it means that eventually we actually reach a state where an exchange takes place. But now the idea of the impossibility result is that there's no way you can reach from a fair state to another fair state where an exchange happened without going through a state that would be unfair. And if once you reach a state that has an unfair state, the other party that's in an advantage, they can refuse to proceed in the exchange, and that would result in an unfair outcome because they can just stop to participate in the protocol. So the idea here is that, well, so you have this literature showing a fair exchange is not possible, but we see fair exchange taking place in blockchains all the time. And the difference here is, for example, this idea of cross-chain swaps via hash time locks is one very popular way to do a cross-chain exchange, where the difference on this line of work is that we assume that the blockchain has a bounded latency. Like by assuming that, we can actually design protocols that take advantage of time bounds to actually execute a fair exchange. But there is concerns in the literature as well that these protocols might be vulnerable to incentive attacks. So when there's work by Zabari et al., where a line of work thinks about, if someone might be bribing a miner to introduce latency, where often we think latency as being a random process, where in this line of work, they think, okay, imagine someone could be bribing miners to introduce latency in the network. Other ways you could actually implement cross-chain communication bridges, and the concern here is that they might introduce a need for trusted third parties. In other cases, you might require an honest majority on the protocol. So beyond that, these protocols often they introduce these additional risks for the users. They are not risk-free for the user, so there is some risk involved, and they introduce some latency. So that comes this idea of shared sequencing, right? What's a shared sequencing would be a system that would allow a block builder to be the same entity with sequencing, who's creating the block on two or more different chains at the same time. And if you could have that property, you could provide synchronization between multiple chains. You could ensure that transactions are executing at the same time on different chains. So let me go over the model that how we model this problem, and I'm going to take the winner-take-all approach that Tim mentioned. So the mechanism design approach, we're going to think about as a combinatorial auction where we have sellers who are in one side are the block builders of one of each chain. In the other side, we have buyers who are the agents who want to acquire block access, and they might want to acquire different combinatorial bundles of the blockchain access. I'm going to assume buyers, they only desire a single bundle. So they have a favorite bundle BI, and they derive some value AI for having that bundle. Otherwise, they don't get any value for getting a particular bundle. And I'm going to assume that these values are independent and drawn from the known distribution. One also property here that I'm going to assume that the sellers have a private value for not selling the item. So they have an outside option to actually not to participate. And if they don't sell in the mechanism, they also derive a value from for not selling the item.
This is both.
What's the S?
Yeah, it's both. Sorry, BI.
B.
But is it known single minded?
Oh, the BI is a non. Yeah, it's private.
Okay.
Yeah, non. The favorite bundle is not known. So the mechanisms we are considering are going to be direct revelations, where the mechanism is going to request what's your reserve price for not selling the item, what's the minimum you want to get for selling the block access on that chain, and the bids from the buyers for different bundles. And the mechanism is going to implement an allocation and a payment rules as in a traditional combinatorial auction. So let me show what's the challenge on the shared sequencing domain. So one way you could, or currently the way if you want to purchase block access on many chains at the same time, you're going to run a single item auction. And let's say for now happens to be a first price auction on each chain. So you're collecting bids on each chain, and these bids, you're going to allocate the item, that particular block access to the highest bidder on that chain. Bitcoin happens to use a first price auction. Ethereum does not use a first price auction anymore, but let's say for now that it does. The problem of the current mechanism is that is a very common problem in combinatorial auctions. It's known the exposure risk, right? If you're going to bid individually on these single item auctions, you have the risk that you're going to buy one of your blocks, but you're not going to buy the other. But even if you buy one item, you're forced to pay for that. So you're going to end in a state where you're paying for something that you don't want, because you actually wanted to have access to both chains at the same time. And it's well known in the literature that in general, the price of anarchy on these problems would be bad, and proportionally is going to grow with the number of of items that you're selling. So the number of chains that you'll be trying to synchronize over time. So now let's go back to the objective. So I showed that what's the challenge for implementing this shared sequencing. So one goal we're going to think about is that we want to improve welfare. In some sense, think that as eliminating the exposure risk that buyers would have. Another goal is that you want to improve welfare. I'm not going to say maximize revenues. Sorry, improve revenue. I'm not going to say maximize revenue, but I'm going to say the revenue should be competitive with the revenue that the sellers would be getting by not participating in the mechanism. Because if their revenue is not competitive, then they would not have incentive to participate on your shared sequencing mechanism. So one way you could implement a shared sequencing would be the following. You have any items and buyers. So for each buyer, we're gonna essentially now run a first price auction, a sequential first price auction, where you're gonna visit the buyers in sequence and let that buyer picks their favorite bundle on the available items that are still unallocated. And for the buyer that receives his favorite bundle, we're going to remove that bundle for the set of available items. And the buyer is going to pay how much he has bid on the auction. So now the very hard question that we're going to face is how we share the revenue, right? Because one goal I mentioned is that we want to incentivize the sellers to participate. And the question is who is going to get which part of the revenue? So one way you could do that is this proportional allocation, where imagine YI would be the revenue that the seller would be getting by selling his item individually in a first price auction, for example. In proportional allocation, what you do is given these YIs, which would be your contribution to the revenue, you partition for seller J. We're going to let I be the buyer that receives the bundle S that contains item J. And down seller J is going to receive this revenue proportional to this quantity with YJ divided by the YKs of where YK is the payoffs of all the other items that are in the same bundle S. So one thing that happens though, however, is that the Bayesian of price anarchy on this mechanism would be unbounded, and one reason is because now the seller has incentive to manipulate his reserve price, because by doing that he can increase the fraction of the revenue that he's gonna receive in the mechanism. In this paper, though, what we do later is, okay, given these negative results, is to think, okay, how could we relax this challenge on revenue sharing on these mechanisms? One observation that you could have for some applications that in many blockchain domains, values are actually not independent. If you have, for example, public mempools, values tend to be very correlated. So the assumption that values are private might actually not hold in practice. Under that scenario, you can actually show that this mechanism that I just showed you would have better welfare. Another mechanism that we look on this paper was this idea of futures market that has been very popular or very well discussed in the blockchain domains, where imagine we had a way where you could purchase access for future blocks even before the creator of that block realizes what his reserve price would be. So you're selling futures access to a blockchain block access. In that case, you can actually design mechanisms that would be ex ante IR for the buyers and sellers and have a good approximation of the optimal welfare. So to conclude, in this talk, I hope I could convey what's one of the motivations for having a synchronization mechanism among blockchains. They can simplify cross-chain, the implementation of cross-chain logic among blockchains. So some interesting theoretical extensions would be to think about buyers that have interdependent values. So in this talk, I assume buyers were independent. Although I gave a motivation of why interdependent valuations could be helpful for actually helping improving welfare. The futures market mechanism I mentioned definitely requires knowledge of the distribution of reserve prices. So one interesting direction is to think about what can you even do if you don't have a very good proxy of what the future reserve prices are going to be. Another question is how you can actually enforce these mechanisms on the actual blockchain. So just think
over time, so we have to get just behind schedule already, but sorry to cut you off.
Yeah, so that just that how you could actually implement these mechanisms in practice. Thank you.